Okay, let's unpack this. We are diving into what is arguably the most fundamental and certainly the most stubborn problem in deep reinforcement learning.
Right.
For decades now, researchers have been grappling with the deadly triad.
The combination of temporal difference learning, off-policy data, and of course, deep neural networks.
It's just a recipe for guaranteed instability, for divergence.
That's the crux of it. When these three elements mix, traditional Q-learning it breaks down.
And the immediate consequence is that practitioners have largely abandoned these really promising, sample-efficient, off-policy methods.
They've fled to the relative safety of on-policy algorithms like PPO, despite PPO's, well, its inherent drawbacks.
Exactly. PPO became the default, the path of least resistance. But today, we're reviewing sources that introduce the parallelized Q network, or PQN, and they claim to have found a simple, powerful, and theoretically grounded solution that finally re-stabilizes these deep off-policy TD methods.
And this deep dive is structured as a formal presentation of our findings directly to you, the senior scientist.
So a precise, objective summary of the work.
Precisely. We'll start with the necessity of this breakthrough, the motivation. Then we'll detail the key theoretical idea, move into the PQN methods, and finally assess the contributions, particularly on efficiency and speed.
All right, so let's revisit the foundational problem here. Since deep Q networks, DQN, came onto the scene, we've relied on these complex architectural crutches just to keep off-policy learning stable.
We have.
It's almost become accepted that if you want the sample efficiency of Q learning with a deep network, you just have to tolerate these fixed overheads.
And those overheads were seen as necessary to manage the sheer volatility of the training process. The instability inherent to Q learning when using nonlinear function approximation really forced the use of two major stabilization tricks.
The first one being the target network.
Right.
The idea is simple. You freeze a copy of your Q network, you use that for calculating the target Q value, and you only update it periodically.
Which is a necessary evil, but one that fundamentally compromises the efficiency benefits you were after in the first place.
How so?
You're using delayed, stale network parameters to calculate your targets. That delayed updating process demonstrably harms sample efficiency.
It's like learning to drive while your only frame of reference is from 5 seconds ago.
Exactly. You're always slightly behind the current state of reality.
And the second major trick, which is just a massive logistical headache, is the replay buffer.
It's indispensable, or it was thought to be, for breaking the temporal correlations in sequential data, which is a critical part of the instability problem.
But this solution introduces, colossal implementation and memory overhead.
That overhead is the key bottleneck in modern large-scale RL systems. In environments like multi-agent RL or the Kraft tax domain, you were talking about replay buffers consuming hundreds of gigabytes of memory.
Hundreds of gigabytes.
So if you're trying to run a highly optimized end-to-end GPU training pipeline, which is the state-of-the-art for speed, the sheer memory footprint of a buffer makes traditional DQN impractical. It forces training off the GPU or requires, massive, expensive memory farms.
It effectively kills the pure GPU training breakthroughs we've seen recently.
It does. And that high cost and complexity led most practitioners to PPO.
Right.
And PPO is successful because it is conceptually simpler to implement in a vectorized context. But we must be clear. PPO, while popular, it lacks the rigorous theoretical guarantees that TD methods have, and it requires notoriously extensive and complex tuning to perform well.
It sacrifices that sample efficiency for simpler implementation and vectorized throughput.
Precisely. So we arrive at the core research question driving PQN. If the architectural tricks, the target networks, the large buffers are just too heavy, and PPO lacks that theoretical grounding, is there a simpler, cleaner way?
And there have been hints before, right? Empirical studies suggesting that maybe just using network regularization like batch norm or layer norm might be stabilizing.
There have. And this work seeks to provide the rigorous mathematical proof that regularization is indeed the key to unlocking these efficient, stable RL algorithms, allowing us to shed all of that heavy architectural baggage.
So this moves us into the theoretical core of the paper, where they really establish the mathematical foundation for PQN.
It does. They use a generalized Jacobian analysis, which is a sophisticated tool for characterizing stability in this nonlinear Markov chain environment.
And for the TD upgate rule to guarantee convergence, to act as a stable learning process, it has to behave like a contraction mapping, right?
Absolutely. The TD stability criterion demands that the TD Jacobian, which you can think of as the effective derivative of the learning update, must be negative definite.
And if that condition holds?
If that mathematical condition holds, the update consistently shrinks the error instead of allowing it to amplify and cause divergence.
The genius here is how they formally decompose that TD Jacobian instability into its two primary components.
Which mirror the elements of the deadly triad.
Exactly.
They define two terms whose positivity leads directly to instability. First, we have the term characterizing instability due to distributional shift.
So this is the error from off-policy sampling.
Correct. The mismatch between the policy you are currently trying to learn, the target policy, and the policy that actually generated the data you're using.
And off-policy sampling is definitively identified as a major source of divergence.
It is. And the second term characterizes the sheer chaos introduced by the deep network itself.
The nonlinear instability.
That's the one. It's zero if you use simple linear function approximation, but it grows really problematic as you add layers and complexity, making the learning landscape unpredictable.
Okay, so we have two distinct mathematical sources of divergence, both baked right into the function we're trying to optimize. How do they tackle this mathematically without falling back on those old DQN tricks?
And this is the surprising theoretical solution presented in Theorem 2. The authors prove that introducing layer norm directly into the Q function approximator mitigates virtually all of the nonlinear instability.
Wait a minute. Layer norm. That's an old trick we use primarily to prevent internal covariate shift during training. How does simple normalization solve a deep, nonlinear mathematical instability problem that has plagued Q learning for 2 decades?
Because it mathematically forces the nonlinear instability term to decay rapidly as the network width increases.
Okay.
They show it decays as O of 1 over the square root of k, where k is the network width. In simpler terms, as the network grows wider, which is a common strategy in deep learning layer norm, effectively linearizes the update landscape. It prevents the network from expressing those highly volatile nonlinearities that drive TD divergence.
That is a fundamental decoupling. It suggests the instability isn't inherent to the update mechanism itself, but to the network architecture under specific conditions.
And layer norm doesn't stop there. It also handles the off-policy distributional shift component. The analysis shows layer norm stabilizes this term by upper bounding the expected norm of the network output, which limits the explosive Q value updates caused by that sampling difference.
So layer norm handles the bulk of the problem, both the nonlinearity and the off-policy shift. But there's a residual term remaining, isn't there?
There is. The remaining instability is dealt with by a final, highly targeted mechanism, applying a small all-2 regularization specifically to the final layer weights.
And that's it.
That's it. This combination layer norm and targeted L2 is proven to yield provably convergent TD algorithms. It completely stabilizes nonlinear and off-policy TD without the reliance on target networks or the logistical nightmare of large replay buffers.
Okay, moving from the theoretical breakthrough to the practical implementation, the parallelized Q network, or PQN. This is the algorithm built on that theoretical certainty.
Right. And it's an online Q-learning algorithm that takes us back to the roots of Watkins' 1989 work. It updates the Q function directly, without delay.
The foundational shift in PQN is how it replaces memory. Instead of managing a large, static, complex replay buffer, PQN relies on massive vectorization.
Synchronous updates across a large number of parallel environments, all feeding data simultaneously into the network.
Now, this sounds a bit similar to how KPO operates, leveraging parallel environments for throughput. But there's a key distinction in the data being sampled, isn't there?
There is. DQN samples from a replay buffer, which averages historic data collected across many different policies over time. The paper notes this is highly offline, and that leads to data staleness.
Okay.
PQN's vectorized, parallel sampling, in contrast, effectively approximates the stationary distribution under the current policy.
So the data is much fresher.
Much fresher. While it's still technically off policy, the data is closer to the policy being executed, which inherently reduces that distributional shift and aids stability. It synergizes perfectly with the layer norm guarantees.
And when we look at the implementation details, the stability mechanism is simply plugging in that theoretical fix.
Precisely. The Q network is stabilized almost entirely via layer norm. While they do test batch norm in some input normalization scenarios, like in CraftTax, the theoretical preference is layer norm.
Why is that?
Because it provides robust guarantees without requiring the extra tricks that batch norm sometimes needs to maintain stability, like those seen in other regularized Q-learning implementations.
Now, beyond stability, this online structure enables a huge efficiency gain that was previously really difficult to achieve with traditional buffered methods. And that's the integration of lambda returns.
The lambda returns, or in-step returns, are a vital efficiency mechanism. They average predictions over time steps.
And traditional replay buffer methods struggle with this.
They do. Methods like retrace, they struggle to reconcile lambda returns with their buffer structure. It leads to very complex, memory-intensive solutions. PQN bypasses this completely. By being online and vectorized, lambda returns are implemented easily, which boosts performance.
And did they see that in practice?
They did. Ablation studies showed that setting lambda to about 0.65 was significantly better than setting it to 0 in the Atari benchmarks.
So the elegance of PQN's methods is its sheer simplicity. It gets rid of the target network parameters, the complex logistics of buffer management. And this online structure provides an immediate benefit for sequence modeling.
Yes, PQN is compatible out of the box with recurrent neural networks RNNs. In traditional replay buffer methods like R2-D2, integrating RNNs is a massive headache.
Because you have to correctly handle the hidden states of the network that generated the data?
Exactly. If you pull a sample from a buffer that's hours old, you have to painstakingly reconstruct the network's internal state at that exact time step.
Which is incredibly complex.
It is. PQN, by always sampling synchronously from the current policy, entirely sidesteps this complex hidden state management issue.
Okay, so this brings us to the empirical validation. If the theory is right, PQN should succeed where traditional methods fail. And the authors first subjected PQN to Baird's counterexample.
Baird's counterexample is a classic testbed. It is intentionally designed to make off-policy TD methods diverge. PQN successfully converged in this domain. It empirically confirms that the regularization and stability mechanisms outlined in Theorem 2 work, even under the most adverse conditions.
That's a critical validation. But the real-world impact is defined by the computational gains, right? The theoretical simplification has to translate into these staggering speed improvements.
And it does. The statistics are transformative for a research workflow. In the Atari suite, PQN proved to be up to 50 times faster than traditional DQN.
50 times?
While maintaining or even improving sample efficiency. Think about that time compression. Training the full 57-game Atari benchmark suite with PQN takes the equivalent wall clock time that it takes traditional DQN to train on a single game.
That's a shift from days of training to just hours. The sources detail that PQN achieved the median score of Rainbow, state-of-the-art method, in only 2 hours.
And Rainbow required 3 full days of training per game to achieve similar scores. This just radically changes the iteration speed for RL researchers.
And what about the memory savings?
They're equally critical, particularly in large-scale multi-agent settings. In a domain like CraftX, PQN saved 31 gigabytes of GPU RAM. But in complex multi-agent RL environments like Hanabi, the impact is immense.
Why there specifically?
When you have 20 or more agents running, a replay buffer can easily consume all available GPU memory. We're talking up to 250 gigabytes. PQN's bufferless design saves that entire allocation, making previously infeasible large-scale experiments possible on standard hardware.
So, looking at performance against the current benchmarks, how does PQN fare against the reigning champion, PPO?
It holds its own and often surpasses it. In Atari 10, PQN consistently outperforms PPO in both final score and sample efficiency. It also surpasses other classic Q-learning variants like double DQN in the same number of frames.
And in the more open-ended environments.
In the CraftX open-ended environment, the PQN RNN variant was more sample efficient and achieved a slightly higher score than the PPO RNN baseline.
What about the truly complex multi-agent setting?
There, PQN VDN is competitive with or even outperforms MPPO and QMix, which are specialized multi-agent methods. This really demonstrates PQN's robustness across a diverse set of domains, including those that demand complex coordination and recurrent memory.
Now, a final point on performance. PQN reached human-level performance in 40 out of 57 Atari games. The slight underperformance in hard exploration games where simple epsilon-greedy exploration isn't enough. That seems to point directly to the clear path for future work.
That's right. The core algorithm is stable and it's fast, but its exploration strategy is intentionally basic. Future research should be able to easily integrate more advanced, curiosity-driven exploration strategies, strategies that were previously impossible to test at this speed and scale due to the instability of the underlying TD method.
So the core contribution is clear. PQN reestablishes off-policy Q-learning as a robust, incredibly fast, and simple alternative to the complexity of DQN and the inherent sample inefficiency of PPO.
It does.
And it does this by proving that architectural normalization, not complex memory logistics, is the key to theoretical stability.
And what's fascinating here, and what should really stick with you, is the implication of that finding. The success of layer norm, the fact that its guarantee essentially linearizes the deep learning landscape enough to stabilize TD, suggests that TD instability might have always been primarily a function of the geometric properties of the network architecture itself.
Rather than an inherent flaw in the off-policy update mechanism.
Precisely. It implies that convergence is highly dependent on how well we can regularize the function approximation. And this raises a crucial question for you, the senior scientist. Given PQN's 50x speedup and its proven stability through regularization, should future research resources shift dramatically? Instead of constantly refining these memory-heavy experience replay strategies, should the priority now be finding the optimal, generalizing regularization techniques that further enhance the geometric stability of these wide deep learning models?